A reflecting telescope is an optical telescope which uses a single combination of curved mirrors that reflect light and form an image. The reflecting telescope was invented in the 17th century as an alternative to the refracting telescope, which, at the time, was a design that suffered from severe chromatic aberration. Although reflecting telescopes produce other types of optical aberrations, it is a design that allows for very large diameter objectives. Almost all of the major telescopes used in astronomy research are reflectors. Reflecting telescopes come in many design variations and may employ extra optical elements to improve image quality or place the image in a mechanically advantageous position. Since reflecting telescopes use mirrors, the design is sometimes referred to as a catoptric telescope. History. The idea that curved mirrors behave like lenses dates back at least to Alhazen's 11th century treatise on optics, works that had been widely disseminated in Latin translations in early modern Europe. Soon after the invention of the refracting telescope, Galileo, Giovanni Francesco Sagredo, and others, spurred on by the knowledge of the principles of curved mirrors, discussed the idea of building a telescope using a mirror as the image-forming objective. There were reports that the Bolognese Cesare Caravaggi had constructed one around 1626, and the Italian professor Niccolo Zucchi, in a later work, wrote that he had experimented with a concave bronze mirror in 1616, but said it did not produce a satisfactory image. The potential advantages of using parabolic mirrors, primarily reduction of spherical aberration with no chromatic aberration, led to many proposed designs for reflecting telescopes, the most notable being James Gregory's 1663 published ideas for what came to be called the Gregorian telescope, but no working models were built until 1673 by Robert Hooke. Isaac Newton has been generally credited with building the first reflecting telescope in 1668. It used a spherically ground metal primary mirror and a small diagonal mirror in an optical configuration that has come to be known as the Newtonian telescope. Despite the theoretical advantages of the reflector design, the difficulty of construction and the poor performance of the specularly metal mirrors being used at the time meant it took over 100 years for them to become popular. Many of the advances in reflecting telescopes included the perfection of parabolic mirror fabrication in the 18th century, silver-coated glass mirrors in the 19th century, long-lasting aluminum coatings in the 20th century, segmented mirrors to allow larger diameters, and active optics to compensate for gravitational deformation. A mid-20th century innovation was catadioptric telescopes such as the Schmidt camera, which use both a spherical mirror and a lens as primary optical elements, mainly used for wide-field imaging without spherical aberration. The late 20th century has seen the development of adaptive optics and lucky imaging to overcome the problems of seeing and reflecting. Telescopes are ubiquitous on space telescopes and many types of spacecraft imaging devices. Technical considerations. A curved primary mirror is the reflector telescope's basic optical element that creates an image at the focal plane. The distance from the mirror to the focal plane is called the focal length. Film or a digital sensor may be located here to record the image, or a secondary mirror may be added to modify the optical characteristics and/or redirect the light to film, digital sensors, or an eyepiece for visual observation. The primary mirror in most modern telescopes is composed of a solid glass cylinder whose front surface has been ground to a spherical or parabolic shape. A thin layer of aluminum is vacuum deposited onto the mirror, forming a highly reflective first surface mirror. Some telescopes use primary mirrors which are made differently. Molten glass is rotated to make its surface paraboloidal, and is kept rotating while it cools and solidifies. The resulting mirror shape approximates a desired paraboloid shape that requires minimal grinding and polishing to reach the exact figure needed. Optical errors. Reflecting telescopes, just like any other optical system, do not produce perfect images. The need to image objects at distances up to infinity, view them at different wavelengths of light, along with the requirement to have some way to view the image the primary mirror produces, means there is always some compromise in a reflecting telescope's optical design, because the primary mirror focuses light to a common point in front of its own reflecting surface. Almost all reflecting telescope designs have a secondary mirror, film holder, or detector near that focal point, partially obstructing the light from reaching the primary mirror. Not only does this cause some reduction in the amount of light the system collects, it also causes a loss in contrast in the image due to diffraction effects of the obstruction as well as diffraction spikes caused by most secondary support structures. The use of mirrors avoids chromatic aberration, but they produce other types of aberrations. A simple spherical mirror cannot bring light from a distant object to a common focus, since the reflection of light rays striking the mirror near its edge do not converge with those that reflect from nearer the center of the mirror, a defect called spherical aberration. To avoid this problem, most reflecting telescopes use parabolic-shaped mirrors, a shape that can focus all the light to a common focus. Parabolic mirrors work well with objects near the center of the image they produce, but towards the edge of that same field of view they suffer from off-axis aberrations. Coma, an aberration where point sources at the center of the image are focused to a point but typically appears as comet-like radial smudges that get worse towards the edges of the image. Field curvature. The best image plane is in general curved, which may not correspond to the detector's shape and leads to a focus error across the field. It is sometimes corrected by a field-flattening lens, astigmatism, and as a methyl variation of focus around the aperture, causing point source images off-axis to appear elliptical. Astigmatism is not usually a problem in a narrow field of view, but in a wide field image it gets rapidly worse and varies quadratically with field angle. Distortion. Distortion does not affect image quality but does affect object shapes. It is sometimes corrected by image processing. There are reflecting telescope designs that use modified mirror surfaces as some form of correcting lens that correct some of these aberrations. Used in astronomical research. Nearly all large research-grade astronomical telescopes are reflectors. There are several reasons for this. Reflectors work in a wider spectrum of light since certain wavelengths are absorbed when passing through glass elements like those found in a refractor or in a catadioptric telescope. In a lens, the entire volume of material has to be free of imperfection and inhomogeneities, whereas in a mirror, only one surface has to be perfectly polished. Light of different wavelengths travels through a medium other than vacuum at different speeds. This causes chromatic aberration. Reducing this to acceptable levels usually involves a combination of 2 or 3 aperture-sized lenses. The cost of such systems therefore scales significantly with aperture size. An image obtained from a mirror does not suffer from chromatic aberration to begin with, and the cost of the mirror scales much more modestly with its size. There are structural problems involved in manufacturing and manipulating large aperture lenses. Since the lens can only be held in place by its edge, the center of the large lens will sag due to gravity, distorting the image it produces. The largest practical lens size in a refracting telescope is around 1 meter. In contrast, a mirror can be supported by the whole side opposite its reflecting face, allowing for reflecting telescope designs that can overcome gravitational sag. The largest reflector designs currently exceed 10 meters in diameter. Reflecting telescope designs. Gregorian. The Gregorian telescope, described by Scottish astronomer and mathematician James Gregory in his 1663 book Optica Promota, employs a concave secondary mirror that reflects the image back through a hole in the primary mirror. This produces an upright image useful for terrestrial observations. Some small spotting scopes are still built this way. There are several large modern telescopes that use a Gregorian configuration, such as the Vatican Advanced Technology Telescope, the Magellan telescopes, the Large Binocular Telescope, and the Giant Magellan Telescope. Newtonian. The Newtonian telescope was the first successful reflecting telescope, completed by Isaac Newton in 1668. It usually has a paraboloid primary mirror, but at focal ratios of f8 a longer spherical primary mirror can be sufficient for high visual resolution. A flat secondary mirror reflects the light to a focal plane at the side of the top of the telescope tube. It is one of the simplest and least expensive designs for a given size of primary, and is popular with amateur telescope makers as a home-build project. The Cassegrain design and its variations. The Cassegrain telescope was first published in an 1672 design attributed to Laurent Cassegrain. It has a parabolic primary mirror and a hyperbolic secondary mirror that reflects the light back down through a hole in the primary. Folding and diverging effect of the secondary creates a telescope with a long focal length while having a short tube length. Refracting. The refracting telescope, invented by George Willis Ritchie and Henry Creation in the early 1910s, is a specialized Cassegrain reflector which has two hyperbolic mirrors. It is free of coma and spherical aberration at a nearly flat focal plane if the primary and secondary curvature are properly figured, making it well suited for wide field and photographic observations. Almost every professional reflector telescope in the world is of the Ritchie Creation design. 3-mirror and astigmat, including a third curved mirror, allows correction of the remaining distortion, astigmatism, for the Ritchie Creation design. This allows much larger fields of view. Dahlkirkham. The Dahlkirkham Cassegrain telescope's design was created by Horace Dahl in 1928 and took on the name in an article published in Scientific American in 1930 following discussion between amateur astronomer Alan Kirkham and Albert G. Ingalls, the magazine editor at the time. It uses a concave elliptical primary mirror and a convex spherical secondary. While this system is easier to grind than a classic Cassegrain or Ritchie Creation system, it does not correct for off-axis coma. Field curvature is actually less than a classical Cassegrain, because this is less noticeable at longer focal ratios. Dahlkirkhams are seldom faster than f15. Takahashi Mulin telescopes are Dahlkirkham instruments with f12 and are highly regarded. They require a corrective for wide field applications. Off-axis designs. There are several designs that try to avoid obstructing the incoming light by eliminating the secondary or moving any secondary element off the primary mirror's optical axis, commonly called off-axis optical systems. Herschelian. The Herschelian reflector is named after William Herschel, who used this design to build very large telescopes, including a 49.5-inch diameter telescope in 1789. In the Herschelian reflector, the primary mirror is tilted so the observer's head does not block the incoming light, although this introduces geometrical aberrations. Herschel employed this design to avoid the use of a Newtonian secondary mirror, since the specularly metal mirrors of that time tarnished quickly and could only achieve 60% reflectivity. Chispeedla, a variant of the Cassegrain. The Chispeedla telescope uses tilted mirrors to avoid the secondary mirror casting a shadow on the primary. However, while eliminating diffraction patterns, this leads to an increase in coma and astigmatism. These defects become manageable at large focal ratios. Most Chispeedlas use f15 or longer, which tends to restrict useful observation to the Moon and planets. A number of variations are common, with varying numbers of mirrors of different types. The cutter style uses a single concave primary, a convex secondary, and a plano-convex lens between the secondary mirror and the focal plane. When needed, one variation of a multi-Chispeedla uses a concave primary, convex secondary, and a parabolic tertiary. One of the interesting aspects of some Chispeedlas is that one of the mirrors can be involved in the light path twice. Each light path reflects along a different meridional path. Stevik-Paul telescopes are off-axis versions of Paul-3 mirror systems with an added flat diagonal mirror. A convex secondary mirror is placed just to the side of the light entering the telescope, and positioned focally so as to send parallel light onto the tertiary. The concave tertiary mirror is positioned exactly twice as far to the side of the entering beam as was the convex secondary, and its own radius of curvature distant from the secondary. Because the tertiary mirror receives parallel light from the secondary, it forms an image at its focus. The focal plane lies within the system of mirrors, but is accessible to the eye with the inclusion of a flat diagonal. The Stevik-Paul configuration results in all optical aberrations totaling 0 to the third order, except for the Petzval surface, which is gently curved. Yolo. The Yolo was developed by Arthur S. Leonard in the mid-1960s. Like the Chispeedla, it is an unobstructed tilted reflector telescope. The original Yolo consists of a primary and secondary concave mirror, with the same curvature, and the same tilt to the main axis. Most Yolos use toroidal reflectors. The Yolo design eliminates coma, but leaves significant astigmatism, which is reduced by deformation of the secondary mirror by some form of warping harness, or alternatively, polishing a toroidal figure into the secondary. Like Chispeedlas, plenty of Yolo's variations have been pursued. The needed amount of toroidal shape can be transferred entirely or partially to the primary mirror. In large focal ratios optical assemblies, both primary and secondary mirror can be left spherical, and a spectacle-correcting lens is added between the secondary mirror and the focal plane. The addition of a convex, long-focus tertiary mirror leads to Leonard's Solano configuration. The Solano telescope doesn't contain any toric surface. Liquid mirror telescopes. One design of telescope uses a rotating mirror consisting of a liquid metal in a tray which is spun at constant speed. As the tray spins, the liquid forms a paraboloidal surface of essentially unlimited size. This allows for very big telescope mirrors, but unfortunately they cannot be steered, as they always point vertically. Focal planes. Prime focus. In a prime focus design, no secondary optics are used. The image is accessed at the focal point of the primary mirror. At the focal point is some type of structure for holding a film plate or electronic detector. In the past, in very large telescopes, an observer would sit inside the telescope in an observing cage to directly view the image or operate a camera. Nowadays CCD cameras allow for remote operation of the telescope from almost anywhere in the world. The space available at prime focus is severely limited by the need to avoid obstructing the incoming light. Radio telescopes often have a prime focus design. The mirror is replaced by a metal surface for reflecting radio waves, and the observer is an antenna. Naismith and Karde focus. The Naismith design is similar to the Cassegrain, except the light is not directed through a hole in the primary mirror. Instead, a third mirror reflects the light to the side of the telescope to allow for the mounting of heavy instruments. This is a very common design in large research telescopes. Karde, adding further optics to a Naismith-style telescope to deliver the light to a fixed focus point that it does not move as the telescope is reoriented, gives a Karde focus. The Karde focus gives a narrower field of view than a Naismith focus and is used with very heavy instruments that do not need a wide field of view. One such application is high-resolution spectrographs that have large collimating mirrors and very long focal lengths. Such instruments could not withstand being moved, and adding mirrors to the light path to divert the light to a fixed position to such an instrument housed on or below the observing floor was the only option. The 60-inch Hale telescope, Hooker telescope, 200-inch Hale telescope, Shane telescope, and Harlan J. Smith telescope all were built with Karde foci instrumentation. The development of XL spectrometers allowed high-resolution spectroscopy with a much more compact instrument, one which can sometimes be successfully mounted on the Cassegrain focus. However, since inexpensive and adequately stable computer-controlled Alt-Arizona telescope mounts were developed in the 1980s, the Naismith design has supplanted the Karde focus for large telescopes.